Well, good morning, ladies and gentlemen. I'm going to talk about, on behalf of our institute, where I'm a director. It's an institute of the Czech Academy of Sciences, as has been said here before. And we are an institute that is combining applied physics and advanced technologies. So in our case, as the name of our institute shows clearly, we are not only developing methods and techniques and associated physical grounds for such a technology. We are also designing instruments that quite usually work also. And of course, we are developing associated technologies for this instrumentation. I will start with several topics that have some overlap towards space technologies, and I will start with quantum metrology. This is a great topic for us. We are involved in a large international consortium that is developing a so-called ion clock. To say something as the background of all this effort, in this diagram you can see how over time the gradual improvement of precision of radio frequency clocks and optical clocks evolved, and it's clearly visible that the optical clocks are really in the lead, and the technology that is actually on the table or which is being developed is a technology of ion clock that are using quantum principles for really generating very precise optical frequencies. The quantum principles means that we are using spectroscopy of a single trapped atom, maybe an ion, and thanks to this we are able to detect very narrow transitions and derive the frequency of the clock laser from this single trapped ion. How does it look like? Here are the experiments that we put together in our lab. It's a very complex arrangement. This design took about 10 years maybe, and we are still evolving. And clearly this is something that is really a laboratory instrumentation. But within the community who are dealing with ion clocks and the synchronization of time and frequency, it is clearly known that the future of this technology will lead to space-borne clocks. Maybe you know the system of Galileo satellites that are based on really very precise time synchronization and generating of precise time signals and referencing of time. It's clearly known that over time, when these Galileo satellites will be replaced by newer versions, the next generation or one of the next generation of these satellites will carry space-borne ion clock. So within this community, we are surely targeting this aim, and it's hard to say how long it will take, but over time, definitely, the design of space-borne ion clock will be on the agenda. And our institute, as I've mentioned, we are really developing very sophisticated technologies that are necessary for such a complex instrumentation. So compared to our colleagues from Western Europe, we are really on the lead that we are able really to put together these technologies, and we don't rely only on components that are commercially available. I don't know maybe how long it will take, but surely this is a great topic. Within our project, which we are considering now, it seems to me that this is such a large-scale project. I'm talking about this ion clock, that it would probably need financing from the whole budget of project that we are considering. But maybe some small contribution would be also useful. There is another large project that is closely associated with the time synchronization derived from the optical clock. And this is a network of distribution of highly precise optical frequencies. The network looks like this. This is under development at the moment. We are again part of the CLONETS European infrastructure project that is putting this together. You can see that our institute in Brno has a connection to Prague and a connection to Vienna. We are now developing or building a next connection to Poland and another to Germany. So this will lead really to a large Europe-wide infrastructure for distribution of highly precise optical frequencies. And this is one of the key purposes for doing this, next to fundamental metrology, is a ground segment for Galileo again. So it's clear that all these ion clocks that would operate in laboratories on the ground will be always more precise than those that are projected to be spaceborne. So there always will have to be some sort of synchronization of highly precise frequencies from the ground segment of Galileo to the satellites that probably in future will carry this ion clock on board. So this network is based on transmission through optical fibers, and there will have to be surely another part of this system that would transmit these highly stable optical frequencies from this ground system towards the satellites. So that's another thing. Then I would mention maybe 3 topics that are a little bit smaller, but also quite relevant. We participated together with the Institute of Atmospheric Physics of the Academy of Sciences on development of one of the components for the ExoMars mission. This is a foldable antenna. This is more or less mechanical engineering, but at least very sophisticated mechanical engineering that was very strictly limited by the weight of the whole system. And this is a folded antenna that is being opened when the ExoMars mission lands on Mars. So it really works, and this is how it looks like. Another quite important technology that we have developed over time in our institute is the technology of optical frequency references. So these are, in fact, references for spectroscopy. These cells are filled with ultra-pure gases, suitable for selecting of special transitions and spectral components that are used for locking of lasers, so for stabilization of lasers. And our technology has developed so far that we are more or less the only producer and supplier of these optical frequency references for the whole metrology community over the whole world. So with a little bit of exaggeration, I would say that the metrology of length, which is based on highly stable lasers, is in our hands. And of course, there is a demand for such highly stable lasers in space applications as well. So especially this reference, this is a multi-part cell filled with molecular iodine. This was designed for the Lazar project, and is supposed to be really the optical frequency reference where the laser source will be locked to. In the next slide, you can see how it looks like, where it is incorporated in the whole setup of spectroscopy that is used for stabilization of the laser. Here is another option that we did. This is a design that has been done in a collaboration with DLR, with the German Space Agency, and it again uses our absorption cell, which is of a different design, but again of multi-part arrangement. So one of the ideas that is behind the very precise lasers stabilized for space applications is one of them is definitely a Lazar project, and the other is again the Galileo, because probably one of the next steps how to improve the stability of radio frequency reference in the Galileo satellites is spaceborne iodine clock. So it means that it probably might be also a laser that is stabilized through spectroscopy in iodine, and the optical frequency is down converted via femtosecond laser synthesizer to radio frequency range. And maybe the last one I would like to mention, we have a group that is dealing with cryogenics and low temperatures, and they design quite a sophisticated instruments for measuring of thermal absorptivity and emissivity. It is a very crucial instrument which is necessary for any design of space applications, because it's important for designing the whole thermal management of a satellite, because under vacuum conditions where the satellite may be illuminated by the sun from one side and be in the shadow on the other side, so there may be really a great thermal gradients, and if you have an electronics on board, the electronics also generate some excessive heat, and the way how to get the heat out and to avoid any unwanted transfer of the heat inside of the satellite, the design of the coatings and the use of materials is very crucial. And our instrument is really designed to measure these parameters and to help the designers to deal properly with the thermal management on board of such a satellite. It has been designed and it is widely used in a collaboration with companies that are designing satellites for the space applications. So that's everything from my side. Thank you for your attention, and I hope that it probably will be useful for our collaborative project. Thanks a lot.
Thank you for the talk. Wait a second. Do you have any questions? Okay.
Yeah.
Related to one of your last slides, are you involved also in Einstein telescope, or do you plan to, because of your expertise?
Which one, please?
Einstein telescope.
No, we are not involved in this.
Thank you.
No.